Good morning, good afternoon, good evening, class. It's Mr. Arosena again. Today we are going to talk about limits at infinity. Don't confuse these with with infinite limits. They're kind of they sound similar, but they're entirely different concepts. All right. So, recall from previous lessons that the limit as x goes to a of f of x is a value of f of x. This caused some confusion with a couple people because they weren't quite sure exactly what the limit of f of x meant. Probably because we talked about as x goes to a, the function approaches a particular value. I guess I didn't make it clear that that particular value happens to be a value of f of x, not a value of x. Now, it is possible to have a limit as x goes to a where the function goes towards either positive infinity or negative infinity. In a case like this, this creates an asymptote, and in particular, this creates a vertical asymptote. Okay, vertical asymptote. So, an example of an infinite limit would be, for example, in the function 1 over x. 1 over x looks like this. Okay. And the infinite limit would be at x equals 0. So x equals 0. Limit is negative infinity on the left side, and positive infinity on the right. Okay. So infinite limits are perfectly possible at x equals a. That's where the function goes towards, either positive infinity or negative infinity. Right, now, what happens when x gets really large? So let's consider a function like this. F of x equals x squared minus 1 divided by x squared plus 1. What occurs as x gets really big in the positive direction? So it's like if it's x is going towards, so x going towards positive infinity. So as x gets ridiculously large, so let's say, I don't know, 1,000,000. So you'll get 1,000,000 squared, so 1,000,000 squared minus 1 divided by 1,000,000 squared plus 1. And this number is going to be very, very close to 1, because 1,000,000 squared is like 1 trillion, and then minus 1 is not going to make a big difference. Divided by 1 trillion plus 1, again, the 1's not going to make a difference. So this is really going to be, you can safely ignore those numbers and just focus on this. So at 1,000,000, this function is effectively equal to 1. So approximately equal to 1. Okay? Now, what if occurs as x goes really big in the negative direction? Well, in the negative direction, kind of the same thing happens because it is x squared, so in the negative direction x is still going to be positive. So x goes to negative infinity. Again, same thing occurs. We'll just pick negative 1,000,000 this time. Negative 1,000,000 squared minus 1 is going to be the same thing as 1,000,000 squared minus 1, and 1,000,000 squared plus 1 is going to be the same as negative 1,000,000 squared plus 1. So this is still going to be approximately equal to 1. So it looks like for this function, as x gets really, really large, so the limit as x goes to infinity of x squared minus 1 over x squared plus 1 is equal to 1. Because it looks like the function is going towards 1 as x gets bigger and bigger. And the same thing can be said for, this is also equal to the limit as x goes towards negative infinity of f of x. Okay. And again, because if it gets really large, then the function effectively becomes 1. Right. Now here's another example. Let's consider this function, 10 to the power of x. What happens to this function as x gets really large? Okay. So what occurs as x gets really large in the positive direction? Well, as x goes towards infinity, well, it looks like my function 10 to the x will also get bigger. Because if I put 1,000,000, 10 to the power of 1,000,000 is really big, so it's going to continuously get larger and larger. So in this case, as x goes towards infinity, this function goes towards infinity as well. I mean, there's no real limit. Now, if x gets really large in the negative direction, this actually has quite a different result. So if x goes towards negative infinity, what will happen to 10 to the x? Well, 10 to the x then becomes 10 to the negative. Well, yeah, 10 to the negative number. So let's say like a million. So if x goes towards negative a million, this will be 10 to the negative 1 million. And this is really just 1 over 10 to the 1 million. 3. And 10 to the 1 million is a really small number, or really large number, sorry, really large number. I'm getting ahead of myself. 1 divided by a really large number is going to be effectively 0. Okay? So in this case, as x goes to negative infinity, my function does have a limit. It ends up being 0. But if x goes to positive infinity, my function doesn't have a limit because it goes towards infinity. Okay? Now when we say x or a limit at infinity, we're really referring to this situation, or these two situations. Okay, so we can say, like for example, the limit as x goes to infinity of 10 to the x, this is equal to infinity, which basically means the function gets big as x gets big. This limit x goes to negative infinity of 10 to the x equals 0. This function says, or this limit basically says as x gets really small or really large negatively, it becomes a really large negative number, 10 to the x approaches 0. Okay. So again, this is the part where these are limits at infinity. In this case, limit at positive infinity, limit at negative infinity. Okay. So we can say the following then. Limits when x goes to infinity. The limit as x goes to infinity of f of x equals L, L being any number, or I guess the limit. This effectively means that as x gets big, the function goes to a particular number L. Okay. And this, oops, I'll go back. This manifests itself effectively as a horizontal asymptote. Horizontal asymptote. Okay. So this limit is really just a horizontal asymptote. And I'll illustrate that using the examples we just talked about. Okay, so the very first one we had was x squared minus 1 divided by x squared plus 1. Then I will draw an asymptote at y equals 1. There we go. Here we go. So here is the red line is my function x squared minus 1 divided by x squared plus 1. As you can see, as x gets big, well, it's not those one. As x gets big, it approaches closer and closer to 1 on the negative side, and this exhibits the same behavior on the positive side. As x gets really big, it gets closer and closer and closer to 1. Okay, so that limit that we calculated as x equals 1, or not, f of x equals 1, the limit equals 1, is manifests itself as a horizontal asymptote on the graph. Okay, let's go back and look at a different, at the other function, 10 to the power of x. Okay, so 10 to the power of x looks like this. As x goes towards positive infinity, it just keeps getting bigger and bigger. But if it's going to negative infinity, it gets smaller and smaller. Eventually it reaches, well, it doesn't actually reach 0. This is just a limitation of the graphing program. It just gets continuously smaller and smaller. Yeah, shouldn't actually reach 0. But again, limitation of the computer program. Alright. Alright. Alright, that's limits. Okay, now let's do an example. Let's find the limit of each of the following. Okay, so this first one, as x goes towards infinity, well, let's say 1,000,000 again. If x goes towards 1,000,000, we can say the following. We'll get 1,000,000 cubed plus 3 times 1,000,000 squared minus 10, all divided by 1,000,000 cubed. Okay. Now, one interesting thing about this is that 1,000,000 cubed in the numerator is going to be so much bigger than every other term in there that we could actually safely ignore this. It's very similar to the previous one where we had like 1,000,000 squared plus 1. The plus 1 doesn't actually matter in relation to the 1,000,000 squared. 1,000,000 cubed is so much bigger than even 1,000,000 squared that we don't have to worry about it. So this is really going to be 1,000,000 cubed divided by 1,000,000 cubed, which is effectively 1. Okay. So the limit as x goes to infinity of this particular equation is going to be 1. Now let's check. Let's check. Let's check it out to make sure we're actually correct. So we have x cubed plus 3x squared minus 10. Okay. Divided by x cubed. Okay, and we're going towards positive infinity. So here we go, going towards positive infinity. There's my function. Starts getting smaller and smaller, getting closer and closer to, it looks like, getting closer and closer to 1 as we get bigger and bigger and bigger. Yeah. Good, so that's correct then. That is correct. Okay. Next. Next one. Oops. Went a little bit ahead. Here I have two trig functions on my last two. Now, this one. This is the limit of x goes to infinity, negative infinity of sine x. This one you don't actually, we can't actually calculate this, but we can think about it. Because what do we know about sine? Sine constantly oscillates up and down, up and down, up and down, up and down like that. Okay, so sine oscillates up and down, and let's say, because we're going negative infinity, so we're going this way. This motion continues in that direction. So it basically means that the limit of sine x as x goes towards infinity, this doesn't actually exist. So it does not exist. Because again, the sine function oscillates up and down continuously. It doesn't actually go towards a particular value. It oscillates between -1 and 1. That's how we go towards negative infinity. Now let's contrast that with the third example. The third example is way different. Because now it's sine x divided by x. Okay? As x goes towards infinity. Well, we know what sine x does. Sine x is always going to be a value between. So this one, sine x, always between -1 and 1, which is great because we know then the numerator will always, but the greatest value of the numerator is 1, and the smallest value is -1. Now as x, well, x can go towards infinity. So as x goes towards infinity, we can approximate this limit as follows. Limit x goes to infinity of sine x over x. We can approximate that. So let's take x to be 1,000,000. So sine of 1,000,000 divided by 1,000,000. Well, again, because we know sine oscillates between -1 and 1, it doesn't really matter what it is. It's being divided by 1,000,000. Anything divided by 1,000,000 is going to be a fairly small number, especially if it's 1. Say 1 divided by 1,000,000 is 0.0000001. Or, effectively, this is going to get closer and closer to 0. Okay, so sine x divided by increasingly large numbers, it'll eventually it'll get very, very close to 0. Okay. Now, let's go take a look at what the graph of this function looks like. So this function looks like this. Sine x divided by x. There we go. And I'm going to change there. Now you can see it. So as you can see, my sine function still oscillates, but as x gets bigger and bigger, the height of the sine function gets smaller and smaller. And it looks like the sine function does go towards 1. Okay. Now what's really interesting about this particular situation is it kind of flies in the face of the definition of what a horizontal asymptote is, because let's contrast it with this one. This function never touches the asymptote. It gets close but never actually touches it. Contrast it with this one, where it does cross the asymptote line. The asymptote line we decided was f of x equals 0. But this function crosses that line continuously. It actually crosses it at an infinite number of times as it gets larger and larger. Okay. But the function still goes towards 0. Sometimes it approaches 0 from the negative side, as shown here. Sometimes it'll approach 0 from the positive side, as shown here. Regardless, it approaches 0 as x goes towards infinity. That's the important part when dealing with limits. Okay. There we go. So here's some examples of how to calculate limits at infinity. Now, here's a couple of helpful hints. Okay, and we've already sort of covered a couple of them. The first one is this. We discussed this a little bit already. As x goes towards either positive or negative infinity, it's safe to ignore lower powers of x, and some constant terms can also be ignored. So like for example, if I have the limit as x goes to infinity of something like this, x to the 4 plus x cubed minus x plus 1, all divided by, let's say, x to the 4 plus 5. Well, x to the 4, as x gets really, really big, x to the 4 kind of overpowers this term, this term, this term in the numerator. So the numerator effectively becomes x to the 4. And in the denominator, x to the 4 is definitely going to always be much bigger than that at some point. Okay, so then you can just safely ignore everything except for the x to the 4s. In this case, the limit of this would just be x to the 4 divided by x to the 4, which is 1. That's it. So as x gets really, really large, you can ignore lower powers of x because the higher power, or the highest power, will basically invalidate all the low powers at x equals infinity. Okay, and that's one easy way of helping you calculate limits at infinity. Just think, I can ignore all the lower powers of x. And the second one is sort of an extension of this one. As x goes to plus or minus infinity and the highest power of x is in the denominator, that part of the function will approach 0. Okay? An example of this would be as follows. Limit as x goes to infinity of, let's say, something like this. 1 over x plus 3. Okay? Well, the highest power of x in this particular part of the function is in the denominator, so this part, as x goes towards infinity, this part goes towards 0. So I can safely ignore this. So the limit just ends up being 3 in this case. A limit as x goes to infinity of 3. Again, because as x gets large, this term goes towards 0. Okay. Now, with these helpful hints, we should be able to calculate most limits at infinity. Okay. There's one question though that will require you to think a little bit, because it'll ask you to calculate the limit using effectively these helpful hints of mine, and then it'll ask you to graph it, and the graph will not give you exactly what you're looking for. The graph is misleading, basically. Okay. Right. Your assignment is as follows. If you have any questions, feel free to come see me in class. Have a good day.